What's up, guys? This is Jahangir from MedPorium, and today we're talking about isomers. So isomers are just going to be these molecules that have the same molecular formula but just different structure. So here's a diagram that it's good to memorize this for the MCAT, but going down through the diagram, our isomers start off with either constitutional or stereoisomers. So constitutional isomers are going to be ones that don't have the same connectivity, while stereoisomers do. But when we go down to stereoisomers, we're broken down to conformational and configurational, which if we need bond breaking in order to invert our molecule, we go to configurational. If we don't, we have conformational, and going down configurational, we have enantiomers and diastereomers. Biggest difference between the two is enantiomers are mirror images, while diastereomers are not, and diastereomers can be broken down to cis and trans isomers. So like I said, this is a good diagram to memorize, to visualize this, because there might be some MCAT questions asking you what are the two types of configurational isomers, which you know, diastereomers and enantiomers. So let's first start off with constitutional isomers. Now, constitutional isomers, they're just going to have different connectivity. So we're going to have a different connectivity. What's an example of this? Well, we can look at something like, let's say we have this guy here, 1, 2, 3, 4, 5. This is going to be our pentane. And the constitutional isomer for this is going to be 2-methylbutane. 2-methylbutane. Now, as you can see, they both have the same molecular formula of C5H12. As you can see, 1, 2, 3, 4, 5 carbons. And our hydrogens, we have 1, 2, 3, because this is a methyl. We're assuming there's 3 hydrogens that we don't show it because this is organic chemistry. We have to make it simple. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And over here, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that follows the molecular formula, and this is what a constitutional isomer is. Now, what about stereoisomers? So stereoisomers have the same connectivity, but they differ in 3D spatial orientation. So our conformational isomers, they are going to depend on the rotation of our sigma bond. So sigma bonds are just the single bonds that you'll see. If you took in general chemistry, this should be a little bit of a refresher for you guys. And with our conformational isomers, we have what's known as the Newman projection. So let's say we have this butane over here, and we're looking from this carbon to this carbon. Well, in our Newman's projection, here is what our front carbon and back carbon would look like. So this big dot right here, that first one right here, that is going to be our front carbon. So this is going to be modeled right over here. And our back carbon is right over here. So I just did, 1, 2 just to show that. So our back carbon is over here. And with our Newman's projection, we can only move the back carbon by 60 degrees. And that's how we get our different positions. So this guy over here specifically, he is going to be known as the anti-staggered position, and he is actually the most stable because there is the least amount of steric strain. So steric strain is caused by having these bulky substituents being close together. Now, as you can see in our Newman's projection for this molecule, specifically for our butane, the most bulky substituents are these methyls, and since they're 180 degrees away from each other, they are the farthest apart that they could be. This results in the lowest steric strain, which creates our most stable molecule, our anti-staggered position. Now, if we move our Newman's projection 60 degrees, we get let me scroll down over here, we get the eclipse position. Over here, they are 120 degrees away. Then let's say we move it one more time again, 60 degrees, then we get the gauche position. So in our gauche position, those bulky substituents are going to be 60 degrees away from each other. Remember, we're only moving the back carbon because that's the only sigma bond that we can rotate is the back carbon. And our last conformation, which is going to be the least stable, is going to be our totally eclipsed. So totally eclipsed. And as you can see with our totally eclipsed, these bulky substituents are the closest that they could be to each other. And since they're so close to each other, we're going to have the most steric strain here, creating our least least stable position in our Newman projection, least stable conformer. So you could think of these bulky substituents as like people that cause a lot of drama or people that want attention. So we need those people who cause the most drama. They don't like each other. We need them to be as far away from each other as possible so they don't ruin the entire vibe. Because if they are as close to each other as possible, they're going to start yelling, they're going to destroy the whole entire vibe, and it's just not going to be a fun scene. So that's what you can think about with these bulky substituents, is that we need them to be as far apart as they can in order to create the most stable conformer. Now, talking about our conformational isomers, we also need to talk about the chair projection. Now, the chair projection is going to be the most stable sort of shape for these cyclohexanes, and what this looks like is these up and down arrows right here that I colored in red, these are known as our axial positions, while the ones going side to side are equatorial. So when we do what is known as a ring flip, so this would be when we flip that, our equatorial positions are going to turn into axial positions. So these are going to turn to axial positions, and our axial positions are going to turn into equatorial positions. So as you can see, I kept the colors the same just to illustrate this. Our equatorial positions over here, like on this carbon over here, flipped and went to the axial position. So when we're doing this flip, if we, let's say this is just 1, 2, 3, 4 carbon, then our 1 is going to flip down, our 4 is going to go up. So this is our 1 over here, 2, 3, and 4. And that is what our flip is going to look like, turning our equatorial into axial and axial to equatorial. So what does an example of this look like? Well, let's just say we have this cyclohexane right here, and our dashes, so dashes are going to be ones that are like the colored in triangles. These are going to be pointing up, while our wedges are going to be pointing down. So, and when you're also putting this on the chair conformation, really doesn't matter which carbons you put it on as long as they have the same position. So this tert butyl is going to have the first priority, second, third, fourth. So make sure that this tert butyl is 1 carbon away from the chlorine. The chlorine is 2 carbons away from the oxygen. So let's say I picked this guy over here. So we have our tert butyl right there. So that's 1. 2, our chlorine, which is pointing down over here. 3, 4, OH is pointed up. And as you can see, when we're trying to find the most stable form of our chair conformation, we need the bulkiest substituent on the equatorial position. The reason why is because this does not cause 1,3 diaxial strain. 1,3 diaxial strain is seen when these bulky substituents or any substituent is on the axial position and they interact with the hydrogens, creating 1,3 diaxial strain. So if we put these bulky substituents on the equatorial position, then this creates a more favorable chair conformation, which is going to be more stable. So over here, our tert butyl is our bulkiest substituent. It is on the axial position. So if we do a ring flip, this guy is going to move down here. So we're still keeping that up position. So our tert butyl is on the equatorial position now, still up. And our chlorine has to be down, but it is going to be on the equatorial position now. Still down, but now equatorial. And over here, our OH is going to be axial now, still pointed up. So over here, we can see that both our tert butyl and our chlorine are on the equatorial position, which is going to be more stable because the only one that has that 1,3 diaxial strain is the OH. In this one, while over here, 2 of our molecules or 2 of our elements, our substituents, our chlorine and our tert butyl were having that 1,3 diaxial strain. All right, so now let's talk about enantiomers and diastereomers. And the first thing we need to talk about when we're talking about enantiomers and diastereomers is chirality. Now, chirality is this idea that our carbon is bonded to 4 different groups. So 4 different groups. And when we have a carbon bonded to 4 different groups, we're going to have a chiral center. So what is an example of, and also with our chiral centers, we need these mirror images that are not superimposable. So just pretty much, mirror images that can't be like, flipped around and then it just creates the same exact thing. So an example of a chiral molecule is, let's say, and for this one I'm just going to label my carbon for this case just to help you guys understand what a chiral center looks like. So let's say we have this guy right here. So this is a chiral center because this carbon is bonded to one hydrogen, one chlorine, one methyl, and one ethyl. All four of these are very unique in their own way, which creates a chiral center. Now, it is important to note that both enantiomers and diastereomers have chiral centers, but enantiomers are going to be mirror images of each other. So to illustrate that, here is our Fisher projection. This is going to be known as the Fisher projection. Let me change my colors real quick. This is known as the Fisher projection, and this basically shows us our substituents, seeing how we can find those R and S configurations. R and S configurations are just a way of us seeing what type of configuration it is based on the highest priority to lowest priority substituents. So highest priority substituents are going to follow this rule. Forgot the specific name, but it is whichever one is bonded to the highest weight or highest atomic number atom. So this carbon right here is bonded to an oxygen. This oxygen has a higher atomic number, has higher weight than our carbon. So this is going to have the first priority. Over here, this carbon is bonded to a carbon that's bonded to oxygen, while this carbon is just bonded to hydrogens. Second priority, third priority. And when we're moving clockwise, this is going to be our R configuration. So I want you guys to pause this video and see if you can find this chiral center based on finding that highest and lowest priority. All right, so now let's go through this one. This OH is going to have first priority. This carbon up here, second, third. We're going to be moving this way, so clockwise again, and this is our R configuration. Now, over here, if we do the same thing, applying our rules 1, 2, 3, we're actually going counterclockwise. And counterclockwise is our S configuration. Same thing over here, counterclockwise. This is an S configuration. Now, I want you guys to look at this left molecule over here and this right one. What can you notice? Well, automatically you can see that they both have different and opposite configurations. So because both of them have opposite configurations, this is an enantiomer because they're mirror images of each other. Like as you can see, the OH over here is on the right, OH over here is on the left. The methyl is on the right, methyl is on the left. Mirror images of each other. This is an enantiomer. Now, what if we're going from this molecule to this one? So our OH is on the right over here, so this is our R configuration, but over here our OH is on the right, that second one. So we know that OH being on the right is an S configuration, and as you can see, when we're looking at these carbons, this top carbon is R, top carbon is R. All right, same configuration, but in our second carbon, we have an R configuration, but over here we have an S configuration, and this is what a diastereomer is. Diastereomers, you're going to identify them by finding two or more chiral centers and only one of them has been switched out. That's all what a diastereomer is. So over here, same exact thing. We have an S configuration over here. We have an R configuration. That is a diastereomer. Now over here, as you can see, if we were just, let me try to black this out to help you guys see this. If we were just looking at this molecule, let's just say the bottom was bonded to a CH2CH3. If we were just looking at this molecule, we see that it went from R to an S configuration, and that's what an enantiomer is. So enantiomers don't need two or more chiral centers, and one of them is only switched. You just need one, but if you do have two, both of those have to be switched. They have to be the opposite. So this is what our enantiomer looks like. Our enantiomers, that's how they look like, is just a complete opposite switch of those configurations. Now this is an important topic to know, and it's like I guess you could say an equation, and in the MCAT it might ask you, it might give you like a molecule and it might say how many different stereoisomers are this from this molecule, like how many different types of stereoisomers there are, and the equation for that is 2 to the power of n, where n is the number of chiral centers. So for our molecule over here, we have 2 chiral centers. 2 to the power of 2 means we have 4 different stereoisomers. And we pretty much showed all 4 of them. 1, 2, 3, 4. Those are 4 of our different stereoisomers derived from our equation 2 to the power of n, where we had 2 chiral centers. So this is a very important equation to know. And in the MCAT, they don't give you any equations, no formula sheets. So definitely try to memorize this one. All right, so now let's talk about optically active compounds, just optical activity in general. So optical activity is basically going to talk about the rotation of polarized light, which is going to be caused by having a chiral center. Now, there are some different qualifications for this. Now, number one, if we want to have an optically active molecule, we need at least 1 chiral center. And I also apologize ahead of time if you can't read my handwriting. But second qualification is we need that chiral center to be non-superimposable and mirror image. We also do not want any symmetry, so no symmetry or no plane of symmetry. So these all sound like qualifications of an enantiomer, and you'd be correct if you assume that, because most, if not all, enantiomers are optically active. There are some diastereomers that are optically active, but enantiomers for the most part will be optically active. Now, compounds can rotate either clockwise or counterclockwise. They can rotate that polarized light clockwise or counterclockwise. So if we rotate that clockwise, see, my handwriting is terrible. Let me just try to put a little bit more effort into writing that better. So if we have clockwise, then this is going to be known as dextrorotary. Dextro, my bad. Dextrorotary. And this is going to be symbolized by that plus sign most of the time, or maybe like D minus. And if we are going counter, I'm just going to put counter C, just counterclockwise, then we are going to have levorotary, which will be known as that minus sign, or L minus, but most of the time you'll see that minus sign, and that's levorotary. Now, these can only be determined experimentally, but the MCAT will tell you if it's dextrorotary or levorotary. It'll just say clockwise or counterclockwise. Dextrorotary, if you want it a little bit more simple, that's going to be rotating to the right. Levorotary, rotating to the left. Now, if we have the same concentration of both levorotary and dextrorotary, this is going to be known as a racemic mixture. Racemic mixture is when we have the equal pairs of those enantiomers, one of them going clockwise, the other one going counterclockwise, and this is not going to be optically active because we have the same amount of both. So one of them is just going to try to go clockwise, the other one's counterclockwise, and they both basically cancel each other out. So this is going to be not optically active. I'll just put OA for optically active. Now, what do these problems look like in terms of optical activity? Well, one of them is actually, unfortunately, it is a math problem. Here's what that math problem is going to look like for optically active, and our equation is going to be specific rotation, which equals observed rotation over concentration times diameter. So in our question like this, we have 0.5, which is going to be our concentration, diameter is 1 centimeter, and our observed light rotated is 20 degrees. So this is just going to be 20 over 0.5 times 0.1, and this is going to result in 400 degrees, and this is going to be in a positive sign. So our specific rotation is 400 degrees. So memorizing this equation is another thing we have to know, because the MCAT doesn't give us formula sheets, so we do have to know this equation. But I mean, it's pretty simple, just plugging in the numbers. And one thing to note is that you have to pay attention to if it is dextrorotary or levorotary. Because if it was levorotary, we would put a negative sign. But this is dextrorotary, thankfully, so it's just going to be a positive sign since it is moving to the right, since it is moving in that clockwise direction. So diastereomers can be broken down to cis and trans isomers, cis meaning same and trans meaning different. So as you can see, these both methyls are on the same side, while these both methyls are on different sides because one of them is a wedge and one of them is a dash. Now in organic chemistry specifically, we have to know E and Z nomenclature. E is just another way of letting us know that we have a trans configuration. So E would mean opposite side of our double bond, while Z meaning same side. So you can think of it like same side is the same side. So I'll just do as our mnemonic same side and of the double bond. Now, EZ nomenclature is going to be seen when we have this double bond and when we're assigning the highest priority. So just like when we were talking about with our Fisher projection, assigning priority to our RS configuration, we're going to use the Cal-Ingold pre-log priority, which the highest priority is just assigned to the molecule that has the highest atomic number. So if we go by that idea that the highest priority has the highest atomic number, then in this molecule over here, if we were to guess if it was E and Z, we need to assign priority first. And when assigning priority, you look left to right of that double bond. So over here, that chlorine has a higher priority than that ethyl because chlorine has a higher atomic number. So this is going to have the highest priority. This bromine is going to has a higher atomic number than the invisible hydrogen that's there. So this is going to have priority as well. And since they're both on the same side, this is going to be a Z conformation. Specifically, this molecule is 1 bromo, 2 chloro, 1 butene. Let me actually move this over here. And that would be our name for this molecule. So I want you guys to pause this video and see if you can identify which nomenclature is this. Is it going to have the E configuration or the Z configuration? All right, so first off, let's assign our priority. So bromine is going to have a higher atomic number. Obviously, it's going to be the first one. And over here, we have a carbon that is bonded to 3 other carbons. So this is going to have the highest priority on this side. Since they're both on opposite sides, this is going to be an E conformation. Now, more specifically, this molecule is 2 bromo, 3 tert-butyl 2 heptene. So that's basically all EZ configuration is. E is going to be opposite side of double bond. Z is going to be same side. Now, our last topic of this video is talking all about meso compounds. So meso compounds are going to have, let me change my color over here. Meso compounds will have a chiral center, so we're going to have a carbon that is bonded to 4 different groups, but that chiral center will have symmetry. So we'll have symmetry. So what does that look like? Well, if we're looking at this molecule over here, we have a chiral center. We have a carbon bonded to 4 different groups, but you can see that we have an internal plane of symmetry. That's a meso compound. Same thing over here. If we flip the script, we still have that internal plane of symmetry, where this top half is the exact same as this bottom half. That's symmetry. That's pretty much all you have to know about meso compounds. Another thing to note, though, is that meso compounds are not optically active. Remember, because our optically active molecules, they need to be asymmetric. But since meso compounds are symmetric, they're not optically active. So that is why meso compounds are not optically active, because they have that internal plane of symmetry. All right, and now let's do some practice. So I want you guys to pause this video and see if you can answer these 2 questions. We'll have a third one as well, but let's just start answering these 2 questions. And like I said, pause the video and we'll go over it. All right, so let's go over the first question. Question 1, which of the following statements correctly describes the relationship between the 2R3R 2,3 dihydroxybutanoic acid and 2R3S 2,3 dihydroxybutanoic acid? All right, so we know that we're dealing with diastereomers. We know we're dealing with RNS configurations. So automatically, process of elimination, we can take out C and D because they're isomers. They're not identical molecules. They have the same molecular formula, but they're not identical, and they're not constitutional isomers because we have RNS configuration. So are they enantiomers or are they diastereomers? Well, if we look over here, we have two chiral centers. So, and one of them has only switched in configuration. So this is characteristic of a diastereomer because only one of our configurations has been switched. Now, number 2, it says a researcher synthesized 4 stereoisomers of a compound with 2 chiral centers. So 2n/2 creates 4. Of the isomers, one of the isomers exhibits optical activity while a mixture of 2 does not. All right, so what do we know about optically active compounds? We know that they have no symmetry, so this excludes Meso Compounds. So we know that A is totally wrong. Now, if we do, since it says one of our isomers exhibits optical activity, that means we have chirality. So C is out of the question because it says there is no chirality. Now it's either B or D. 2 compounds in the mixture are diastereomers. You know, that could be true, but B is the more correct answer because this answer doesn't cover the fact that this question said while a mixture of 2 do not. So the only way we have a mixture of 2 isomers that don't contribute to optical activity is if one of them is dextrorotary, the other one is levorotary. One of them is positive, the other one is that negative sign. They're gonna be 2 pairs of enantiomers. Since they mix together, they do not have optical activity. While one of them needs to have optical activity, which is at least one of those enantiomers. So the answer for this one is B, because this talks about while a mixture of 2 of them does not, which if we see a mixture of 2 that don't, automatically you need to know that as a racemic mixture. All right, now for our final question. Which one of these is a meso compound? Now I want you guys to pause this video and see if you can find the correct compound. All right, so let's go down through each of these answers, and we have to look at our internal plane of symmetry. So if we're looking at these internal plane of symmetries, we can see that D is automatically correct. I mean, it literally has a hydrogen. There's no OH on the other side. That is not symmetric. Now, C and B look like potential answers, but the reason why they are wrong is because we have a wedge pointing up and a wedge pointing down. So those are not going to have symmetry. But if we did, like for example, if we had something like this, just assume that that's a CH3, we have a wedge right here, and we have a dash on that OH. On the Fisher projection, those OHs are going to be on the same side. So we want those OHs to be on the same side. Only answer that gives us that, to give us that internal plane of symmetry, is A. So A is the correct answer because all of them have chiral centers, so we don't have to worry about that. But A has that internal plane of symmetry, which is why A would be the correct answer. All right, and that concludes our video on isomers, optically active molecules, as well as some real-life MCAT problems. Now, hopefully this video was helpful to you guys, and if it was, please consider subscribing, liking, and leaving a comment down below on any other topics you'd want me to discuss. And as always, a Pomodoro a day will make you a doctor someday. I'll see you guys in the next one.